Welcome to the third video of your Monte Carlo simulation and modeling series, in which I will introduce the concept of Monte Carlo simulation, a method that derives its name from the city of Monaco and its associations with casinos and gambling. However, its core idea involves using random trials to explore the behavior of complex systems. I will begin by establishing an intuitive understanding of the fundamental principles behind Monte Carlo simulations. Furthermore, I'll demonstrate how you can put these principles into action using Microsoft Excel. This will include a guide on simulating data that are distributed binomially. Let's start with something slightly abstract, but undoubtedly familiar to you all. Imagine you are required to determine the area enclosed between a function and the horizontal axis of a coordinate system, but you do not have the knowledge of integration. Or you might in fact be dealing with a function that lacks a closed antiderivative. What you can do though is applying the function itself to various values. So, for instance, you can calculate that a graph starts in the origin and that f of 4 is 48. Consequently, you can deduce that the rectangle enclosed between these two corner points measures 4 by 48 equal 192 units. Now, visualize placing a randomly positioned dot within this rectangle. The dot might land between the curve and the horizontal axis, precisely within the region whose size we aim to ascertain. To highlight this, I'll designate the dot as green. Next, let's position another dot. In this instance, it lands above the curve, outside our target area. I'll shade this dot in gray. We can repeat this over and over again. Assuming that these dots are in fact placed randomly, what is the likelihood of a dot falling beneath the curve? This probability intuitively aligns with the ratio of the area underneath the curve and the total rectangle size. Therefore, by consistently placing dots across the rectangle in numerous iterations, distinguishing between those below and above the curve, we can approximate the area of interest by multiplying the proportion of green dots with 192, the area of the entire rectangle. How can we practically achieve this using Excel? To begin, I need to establish the range of coordinates for our random dots. The value of x is confined within the interval 0 to 4. I find the corresponding y values by calculating 3 times x to the power of 2 and get 0 and 48, which defines the interval for y. The chart on the right is, by the way, just for illustration. We do not need it for the actual simulation. Let's move on to generating random values. Within Microsoft Excel, you'll encounter two functions capable of doing that. In this case, I'll use rand. Note that you need to both open and close the parenthesis for it to operate, although it does not accept any parameters. Rand generates values uniformly distributed between 0 and 1. It updates every time I press F9. To obtain values between 0 and 4, I can multiply the function by the upper limit. The same logic applies to y, which I need to range from 0 to 48. Now, with these random coordinates, one dot has been generated. It is important to recognize that x consistently resides within the area of interest. However, determining whether the y-coordinate lies below or above the curve requires a logical assessment. This can be easily done using an if function. If y is less than or equal to 3 times the corresponding random x to the power of 2, the value 1 is assigned, indicating that the dot has landed within the area of interest. Conversely, if the condition is not met, a value of 0 is assigned, denoting that the dot missed the target area. I now replicate this process across a substantial number of iterations, let's say around 1000 times. Following this, I proceed to divide the sum in the hit column by the total number of iterations. By doing so, I arrive at the proportion of hits, a value that can be directly multiplied by 192, the size of the rectangle around the curve. The outcome is an approximation for the integral we seek. Obviously, we do know that the integral is 64, and our estimate is somewhat off. With each press of the F9 key, I receive an update revealing how our approximation orbits around the correct value. Nonetheless, it's evident that the deviation can be substantial. Can we make the estimate more stable with a larger number of iterations? Yes, we can. The law of large numbers tells us that as the sample size increases, the likelihood of significant deviations from the actual value diminishes. Let's try 10,000 iterations. That definitely gives us more consistent results, but maybe we want more precision. So what about 1 million? That gives the computer some work to do, which is an argument to not go too crazy. But now we find the result to be reliably very, very close to the true number of 64. Let's move to a second example, which carries a bit more practical relevance. Imagine overseeing a gas station equipped with 10 electric charging points. For planning purposes, you aim to simulate the number of available charging points at the moment of an electric vehicle arriving. To accomplish this, we can use the function rand_between. This function requires two parameters, namely the lower and the upper limit. In our case, this would be 0, i.e. no charging points available, to 10. The function generates integers at random within this defined range. For this demonstration, I'll conduct 100,000 iterations to simulate the number of available charging points. To analyze the outcome, we can identify specific empiric quantiles, such as the 5% and 95% quantile. Why? This is fairly standard because it tells us the range in which the vast majority, 90%, of all observations fall. To achieve this, I'll use the function percentile_inc. However, what we get looks a bit suspicious, to be honest, so we best analyze the distribution in more detail. We can have simulation results from 0 to 10. And with the help of the function countIf, we find that these results are fairly uniformly distributed. Actually, this comes as no surprise, given that this is precisely the nature of rand_between. The function generates integers with a uniform distribution. However, does this align with our specific context? Only if we have absolutely no prior information about our charging points. Yet, if we knew, for instance, that each charging point is occupied 60% of the day, this would imply a 40% availability probability. And if we knew that, we should by now have developed a reflex telling us that the number of available charging points should be binomially distributed. But can Excel generate binomially distributed numbers? Yes, it can, which brings us to the video's next subject. First, I will show you the formulas that we need to stack up and explain what I did afterwards. I'll delete our previous simulation and start with the function binom_inf. The number of trials is 10 because we have a maximum of 10 charging points, and as probability we use 0.4 for this example. But instead of providing a fixed quantile, I let the quantile be generated randomly using rand. What we do here is we pick with equal probability a value between 0 and 1 from the vertical axis of a cumulative binomial distribution. We then apply the inverse binomial distribution function to project that random value onto the horizontal axis. This way we create binomially distributed x values with some values occurring more often than others. And this is what we get by spreading the formula across all iterations. So, potential success. However, in case you are wondering whether we really needed to do this, your skepticism is justified. We did not. Instead of finding the 5 and the 95% quantile by empirically analyzing the simulated numbers, we could have just used the inverse binomial function and calculate the theoretical 5 and 95% quantile for n equal 10 and theta equals 0.4. And instead of empirically counting occurrences, we could have just used the binomial function, calculate probabilities and multiply them by the number of iterations. So, what is the point? Consider a scenario where our confidence in theta is somewhat uncertain. What if theta experiences fluctuations so that the best we can provide is a range, perhaps spanning from 0.2 to 0.6? In such a context, no predefined function is readily available. Nonetheless, we can still simulate values. To achieve this, I draw upon the function employed previously while introducing an additional element. I also generate the probability term randomly, restricted within the bounds of 0.2 to 0.6. For implementation, I again utilize the rand function, which, remember, yields values within the 0 to 1 range. By multiplying this with the difference between the upper and the lower bound, I obtain values ranging from 0 to 0.4. Adding the lower bound value of 0.2 to this result generates random values spanning from 0.2 to 0.6. Let's take a look at the results. The quantiles change somewhat, and we see that the distribution becomes visibly wider when theta is randomly generated. This is understandable, considering that we are now dealing with not just one, but two elements of randomness. This dual layer of uncertainty naturally contributes to an overall increase in the level of unpredictability. An even wider range for theta causes the overall distribution to become even flatter. In the extreme case of theta being unknown, i.e. possibly ranging from 0 to 1, we obtain a uniform overall distribution. At this point, I'd like to take a moment to pause. Instead of going further into additional examples and technical details, which I will do in the next video, I want to summarize the essence of Monte Carlo simulation. Number 1. We encounter a situation where we understand the boundaries of the problem, but the finer details of how they interact remain unclear. Additionally, the absence of historical data precludes empirical insights. Number 2. With a lot of thinking, we might be able to work out all the mathematical interdependencies, but that may be hard or impossible to achieve. Number 3. Instead, we simulate values within the established problem boundaries. With this simulated data, we are creating something like a myriad of potential futures. Thousands and thousands of outcomes that are consistent with and possible within our understanding of the situation. These artificially created data enable us to apply basic descriptive statistical methods, such as determining quantiles or distributions, like I've done in the example, but we could also calculate arithmetic means, variances, medians, draw pie charts, and so on. We certainly need a bit more practice to master Monte Carlo simulations. However, at this point you should be able to apply your knowledge to some simple problems similar to what you've seen in this video. So at this point, I'd like to thank you for watching, and I hope you're looking forward to the next and final video on the subject.